today this lecture is regarding a case study. So this case study we have performed to install a hydrokinetic turbine. We have planned this exercise in Baraka River, Jharkhand. Now this particular area, it belongs to Pastmara, Tukipur and Bhurahi and Rangamatia village under the Fatehpur Gram Panchayat, Tundi block, Dhanbad district, Jharkhand. So while we have selected this particular area, actually we have made certain survey where we can perform such type of exercise. Actually, after doing lots of experimental study, then we felt that some of the study is required in the real field. So with the help of our students, our IIT ISM students, we try to find out which is the river location where we can install this type of exercise and we can do the exercise. So we found out that this is the area where a river flow is available throughout the year, and this area is very near to few villages which is kind of off grid. So proper electricity was not there or not sufficient. So we thought that such type of exercise can be done here, and so we did this exercise in this particular area. So before going into this exercise, some preliminary study we have performed. First one, after getting the information about this area, so we actually downloaded some SRTM data which is available in the internet, freely available in the internet, and we have downloaded this SRTM data, and then we have we have collected the population data. The population data, actually we planned this particular exercise during 2017-2018. So during that time we found out that this data, the population data which is actually available, that is of 2011 census data. So in 2011 we collected the whole Jharkhand data, and then we found out some of the data of the block wise data, and from there we felt that that we should perform some survey. So here we did some survey in this area later on with the help of our students and with the local people. So we found out that how this 1593 people resides in almost in this area with a 226 household, and after downloading the SRTM data from the internet, we try to analyze the data of this particular catchment area, and we delineated the catchment area through the ArcGIS, and we found that 2.36 kilometer square area is contributing to this river, that particular patch of this river, and this was the extensive rural area. And we have discussed with the local people regarding their economic status and their accessibility to the power, accessibility to the road and the water resources. We try to collect different historical data of the water resources, because the area, that particular spot which we went there, which we have located for this particular study, that we found out that this is ungauged. So the data which is usually the river flow data which is available in CWC website, whatever we have discussed yesterday, so those type of data is not available. Data was not available back then, so we planned that we will be collecting the data. But after observing, after discussing with the local people, we found out, we decided that we will not go for collection of the data during the monsoon season, because monsoon season the river is very rough and it is hardly difficult to collect the data. It will be risky with our limited resource. So we planned that we will be doing this exercise during pre-monsoon or post-monsoon season. So accordingly, we have planned, and in the meanwhile, we have found out what will be the we have done some GIS analysis to find out the water distribution network with a different stream order. So first order, second order, third order streams, such type of stream order we try to delineate out of the SRTM data, and then with this data basically we have an impression that how this particular river will be behaving. Based on the shape of the catchment, we can understand whether any kind of flash flooding possibility is there, and which type of behavior your catchment will be giving, what will be the shape of a hydrograph. All these things we can understand. So accordingly, we have prepared ourselves to proceed further. Now you can see in this particular picture that one of our students, he is standing inside the water, and he is some local people who are actually in the deep water, and across this particular river we put some rope, and there are some marker on this rope. Using that also we can find out what will be the distance from the bank to this particular part, or these local people, they will be swimming across the river, and we can get the distance from the bank at that particular position, and he is holding a rod through which actually we can get what will be the water depth at this particular level. So similarly, far from this bank, that is not possible for our students. It was risky, so we handed over this rod to them, and we trust them whatever value they were telling. So accordingly, we have found out the riverbed profile also. So in this manner, basically we collected the data, and we found out this is a example of location B, and this is the location A. So at this part, this is the location B, and this is the location C. So location B river cross section we have found out in this manner, and location C, you can see how much it is rough, and location A, actually location E is not on the river, it is the picture of the village where we did the study. So some of the pictures also shown here. So you can see these small huts was there. So it is a really rural area, and we have discussed with the people. So we have discussed some historical events also with the people, and then we thought that even if we cannot go for the field study, actual field study during the monsoon season, but we can have some idea about the river. So we, during the monsoon also, we did some of the experiments, but that is erroneous, but we got some idea. So erroneous means we have thrown some of the floating device in the river, and then that particular floating device, we marked the area, consecutive area, and that particular consecutive area we knew the distance between these two area, and we, with the help of the stopwatch, we try to measure the time during which the floating device was traveling from one point to the another point. In this manner, we try to get some idea what will be the velocity. So the velocity, and we performed such type of exercise during 2-3 years, few times during 2-3 years, and we come up with a conclusion that the river velocity will be varying at this particular position, location B. River velocity will be varying 0.88 to 1.88 meter per second. Even if 1.88 meter second is not that much intensity, but the river bed was very slippery, so it was difficult to stand there and to perform the exercise with the facility we had back then. So the river stage we have found out it was 69 meter approximately, and we have measured the location B during our December 2020. And we, after that, what we did, you can see this particular figure, how actually we performed our exercise in December 2020, that means post monsoon season. So after that also we have performed some other exercise. We tried to collect the silt which is present, which was carried by the fluid of the river. So that silt analysis we have done this actually with this particle size, sediment particle size we have measured, and that sediment corresponding to the sediment particle size, we try to find out what will be the average erosion rate density, and then we have used the data to find out what will be the probable erosion of this the probable erosion of this that may happen in the turbine blade. So those type of exercise also we have done, but that is in different turbine. So this has been actually this exercise has been done actually in March 23. I have given the this particular picture of March 2023 and March 2000. It is a really hot time there, the pre-monsoon season. So we have we discussed that we have collected some 2011 census data. So 31.9 million people of Jharkhand, that was annual power consumption was given as 885 kilowatt hour per capita. Now with respect to that value, basically we try to find out what will be the power requirement of each and every person of this particular area, study area. So correspondingly, during that time, we found out the data which was available up to 2011, that, and when we did this exercise during 17, 18, 19 in this area, or maybe in 20 and 22. So we found out that this population number of population that has been changed. So we thought that that particular exercise, that particular identification of the number of population, it will be difficult. So again we did the survey there, and finally we came up with the conclusion that we should go with the population growth for next 20 to 30 years. Then we should project the energy requirement of this particular area. So accordingly we did some exercise, and this is one of the result of this exercise. We have used variable distribution to find out what will be the population growth in next 20 to 30 years. But that exercise was based on the 2011 data. So actually back then in 2020, so this value was already crossed 10 years. So next 20-year data, that was this is the region where red line is there, and this is the region with a green line, which is actually based on the population back then. So we have got an idea. So how many number of people will be staying here if everything goes normal? What should be the energy requirement in this particular area? As well as we have discussed with the people throughout a day, what is the amount of the power which is required for this particular area. So accordingly we have made a profile of daily load profile of this particular area. So correspondingly, basically the average value that has been distributed, and we found out the intensive most value requirement of this area, even if we install this particular type of turbine or particular type of energy generation system. So in this way, we were able to identify what should be the energy requirement criteria of this particular area. So we have used all this data, and we have put this data in Homer software. But before going into the Homer software, what we found out, that not a single turbine is capable of giving that much of energy to fulfill the energy requirement of this area. So multiple number of the turbine may be required to be installed. So the thing is, how to place those turbine, how many number of turbine is required, and how to place them. So to perform this exercise, we first do some laboratory experiment as well as simulation, numerical simulation, to find out what is the influence of the one turbine to the another whenever multiple number of turbines are installed in array. So this exercise initially we have started with 2 turbine. So in our laboratory setup you can see this laboratory setup, 2 turbine can be installed on the flume, and we can find out the power produced by this particular turbine corresponding to a fluid flow velocity. So that exercise we have done, and we have done this similar exercise in the ANSYS software. And in the ANSYS software, basically we validate, we have fixed the ANSYS setup for this analysis, and we try to validate with the experiment result. So with sufficient validation, we fixed the ANSYS setup, and then we have increased the number of the turbines with different other formation. So that is the different study. But here you can see this is the hydrokinetic. This is we have for this analysis we have used 7S hydrokinetic turbine, especially specifically to say it is a helical based 7S hydrokinetic turbine, because out of 2-3 7S hydrokinetic turbine, what we have discussed yesterday also, that helical hydrokinetic turbine is performs best. So this helical hydrokinetic turbine we have used here, and you can see this is the laboratory experiments laboratory setup available in our laboratory setup. So here is the flume, and fluid was actually coming from this distance from fluid flow direction was from this direction to that particular direction. And then there is a trolley which is installed in the upper rack of this turbine. This trolley can be moved along the length of the flume, and in the trolley torque measuring devices are installed. So trolley can be moved, and as well as this turbine can be moved in the trolley can move in the x direction, that means along the direction of the fluid flow, and this particular part of this trolley it can move in the x-axis, y-axis as well as z-axis. So in any depth and any position of the river, I can put my turbine. So that particular facility was available here in our laboratory. So with this we did our experiment, and we try to find out the what is the performance of the turbine, and accordingly we have tried to collect the data, and we validate it with the our simulation result. After simulation, then we increase our turbine from 2 to 3. So during that time, basically we have changed the formation of this turbine from triangular to the staggered array, and we try to find out the performance of this 3 turbine at a time. And we found out that triangular turbine, it is triangular formation of the turbines, it is giving better result. Now meanwhile, whenever we have used whenever used 2 turbine consecutively, so we have tried to increase or decrease the actually we can increase the distance between the 2 turbine. So actually we have tried to find out what should be the inter turbine distance between the 2 turbines, so that we can find out what should be minimum gap we need to keep. So we found out we have in this manner we keep the distance 2.5D to 5.5D, almost 2.5D, 3D, 3.5D, 4D, 4.5D, 5.5D, such thing, and D is the diameter of the turbine. So in this manner, basically we try to increase or decrease the distance, and we try to find out when the 2 turbine will be giving the result. Similarly here also we have tried to increase the distance between the turbines. So there are 2 things. One is the formation of the turbine, and second one is the inter turbine distance of the turbine. So formation of the turbine, just I told you, that will be the either triangular formation or staggered formation. And distance, similarly we have increased and decreased the turbine distance, and accordingly we found out that this at 4D distance, either it is in inline array, that means 2 turbines we are using, or we are using 3 turbines in staggered formation or triangular formation, it will be giving the better result during the 4D distance only. but within that time also which particular formation will be giving better result. So we found out the triangular formation will be giving the better result. So you can see this particular figure. So these first three, rotor 1, rotor 2 and rotor 3, this particular figure corresponding to the 3 turbine, and here you can see that 4D, that means this brown one, it is giving the better result. Or even if the result is actually this brown one and green one, this is almost similar, but the brown one is giving me better. So even if you are increasing your turbine distance from 4D to 5D, maybe 6D, so it will not have that much impact. That means performance will not increase. So better keep it as 4D. Here I have produced some selected graph, otherwise it could have been clumsy. So I have not produced here 2.5D, 3.5D, 4.5D or 5.5D graph, only 3, 4 and 5D graph. So here also you can see this is the graph. Here this particular graph corresponding to the 2 turbine. First one, actually here I have shown you that particular graph which is corresponding to the 4D gap, because already we have established that 4D is the base distance, inter-turbine distance. So if one single rotor is present, then at 4D distance, this is the circular one in the graph, that is CP versus TSR graph, and that is the performance graph. And this triangle is the rotor 1, triangle is the triangle represent to the rotor 2, and whenever we are combining these two, so this after combination it will be giving you this particular graph, and there is some experimental value. So L equal to 4D rotor 1, L equal to 4D rotor 1 experiments. So this circular one and this black dot, so you can see these are the values almost this is coming within a similar zone. But here also I would like to tell that sometimes we found out some outlier. So with this particular outlier also, outlier data also I have eliminated those data, because that was the erroneous data, or sometimes that data is not suitable. So to perform this experiment is lots of time was required. Now with this help of this data, basically what we did then we have taken those data that if we so far what we found out that inter-turbine distance should be 4D, and what will be the capacity of a single turbine, what will be the requirement of a more number of this particular area. So if requirement of the particular area, we decide the requirement of a particular area, then we get to know how many number of the turbine is required to fulfill the energy demand. So accordingly, what we found out that say 20 number of turbine is required. So 20 number, or maybe 20, so we go for the 21 number of turbine, because 21 number already we have tested 3 turbines in a array. So we have found out the triangular array is the best. So triangular array we can establish 21 number of turbine, and 3 at a time we can put it in a triangular, next three like this. So that particular array formation with a L equal to 4D distance, we can place it in our river patch. That particular patch already we have studied, and accordingly we can place it here, and definitely we can get the energy which is required for this particular community. So this is one way of giving a solution to them. Now after that, there is a provision in the Homer software. This is Homer software also calculate some techno-economic analysis for the hybrid energy system also. In hybrid energy system, say we are planning that not only this hydrokinetic turbine, but also if we are trying to put say wind turbine, say maybe some solar panel, say maybe some biomass system, so which will come under the renewable energy sector. So if we make some combination, so whether it will be able to give me some economical friendly system or not. So this is called hybrid energy system. So we did that particular exercise also. So with the hybrid energy system, so you have to feed the what will be the cost of a unit of a hydrokinetic turbine, what is the installation cost, and what is the running cost, as well as what is the installation cost of a solar power solar unit, what is it, what is the unit cost of a solar unit, what will be the running cost of a solar unit, similarly for the other energy generation unit. So after feeding all this data in the Homer software will do certain calculation, it will optimize value, then it can give you, okay fine, instead of putting 20 or 21 number of hydrokinetic energy system, you can put say 10 number of hydrokinetic energy system, maybe 4 panel of solar panel, maybe one wind turbine of a certain capacity, of certain diameter, and as well as 2 unit of biomass system, it may work. So we have the locality, there are cattle is there are agriculture is also going on, so you can get the material for required for the biomass unit, as well as sufficient. This a particular area, it is located in such a area where almost all over the year you will get sufficient amount of the solar energy. Similarly, the river source also available, sufficient velocity also available. So if we install say 10 number of turbine, so ultimately with the help of all these things, with the combination of all these things, we can produce the energy which will be most economically viable. So the energy cost will be the least. Otherwise we can go for the 20 number of turbine, so it may be a bit of costly. So this type of analysis can be done in the Homer software. So for a particular community with the available resource, which type of combination you can select, that also can be done through the hybrid energy generation system analysis in the Homer. So similarly, or otherwise we can go for analyzing single type of energy generation unit, say hydrokinetic turbine generation unit. With the help of this also, I can go for only one kind of energy generation unit and I can see. So here basically we did our analysis for this particular area for only hydrokinetic turbine analysis physically, but theoretically we have done this particular analysis for hybrid energy generation system, and we have published our literature in this technology analysis of a micro hydropower plant consists of hydrokinetic energy in a different formation of for a rural power supply. We have published it in 2021. As well as I have told you, some erosion analysis also we have performed by collecting the data of river flow, what should be the sediment size, and corresponding to the sediment, corresponding to that particular velocity, whenever it will be impinging on the turbine blade. So how it will impact the turbine blade, what will be the material removal out of this turbine blade. So this type of analysis also can be done, and that we have done for the other type of turbine. So in this type of case study also can be done. And with respect to the futuristic demand, so what will be the for future power requirement, which type of analysis and what type of facility to be created, that also can be done. So this type of analysis already we have reported in few papers. So here I have mentioned in the paper. So that is available in the internet. If you can ask, I can also give you those data later. So with this I conclude my lecture, this lecture series. Thank you. If you want to know anything, you can ask me.